Assalamualaikum to my panels. My name is Sofia Nadhirah binti Amluddin. Today I will present my FYP2 project which entitled The Voltage Variation Analysis for Solar Power Plant in UTEM. My supervisor is Dr. Aida Fazliana binti Abdul Kadir. Below I provided my email and handphone number for you to contact me. The project background. The project background for this title is the range of voltage regulation set by TNB is set to not overflow in a power generation and would not affect if minor changes were to occur. Previously, several blackouts occurred which relates to the large disturbance related to voltage in load of a PV generation. On a steady state condition, the grid connected PV inverters must have the ability to absorb and supply power from the grid in order to maintain the voltage stability. Problem statement. The problem statement of this project is most grid-connected PV inverters are only set up to inject power at unity power factor. The plant should be able to supply rated power output at any point between the limits of 0.85 power factor lagging and 0.95 power factor leading. It will reduce the power factor when the grid supplies less active power but the same amount of reactive power. The objectives of this project is to determine the voltage variation analysis for solar power plant at FKE UTEM, which has done in FYP1. Second is to model grid-connected PV inverter controller that could absorb and supply reactive power. To study the capability of the voltage variation of the grid-connected PV inverter controller to absorb and supply reactive power following the Malaysian grid code requirement. Last is to study the impact of voltage variation of the grid system to the PV plant with reactive compensator, which is capacitor bank. The Malaysian Grid Code MGC. So this is the requirements needed to comply. The figure 1 shows the P versus power factor. Figure 2 shows the voltage versus power factor. So the Malaysian Grid Code requirement is a bar that controls the usage of electricity to ensure that no power is wasted and to maintain efficiency for all users all around Malaysia. The scope of this project is steady state condition, one bus system, capacitor bank as the reactive compensator, and uses MATLAB simulating software. So the methodology of this project, solar PV connected to grid system which designed in MATLAB simulating software consists of a PV panel, DC to DC boost converter, inverter, filter, load, and main grid as shown in figure 3, which I will show later. Control system that were designed are VF, inverter drip control, which has frequency control loop, PDC, power control loop, and voltage control, which is shown in figure 4 to 7 respectively. So this is the main grid of my system. So this is the control loop. This is the VF inverter drip controller. For the first control, we have the frequency control loop. Second is the PDC, the DC active power control loop. And lastly is the voltage control loop. The phase lock loop control. The phase lock loop control, or PLL, is to match the frequency of the inverter with the grid and lock onto that frequency, which is 50 Hz. Figure 8 shows the PLL design in MATLAB Simulink, and Figure 9 shows the basic construction of a PLL. Next is pulse width modulator PWM generator. It is to convert DC source generated by the solar panel array to an alternating current for the electrical grid. So figure 10 shows the PWM generator which designed in MATLAB Simulink. Harps transformation. It is to transform the three-phase instantaneous voltages and currents into the synchronously rotating reference DQO frame. It is more convenient to compute and control. So figure 11 shows the current Parkes transformation and figure 12 shows the voltage Parkes transformation, which both designed in MATLAB. So this is the parameter of the grid connected PV system. Table 2 shows the parameter of controller gain for VF through control, which has the frequency control loop, PDC control loop, and voltage control loop. So the results are, I have made a comparison between the grid system with no capacitor bank and 500 kVAR capacitor bank connected to the grid system to see the compliance of the grid system to the MGC requirement with the voltage stability. So table 3 shows the result with no capacitor bank. This is the result of voltage and current at the grid. Second is the result of voltage and current at bus 1, and the result of real power, reactive power, and power factor. Below are the result that I have obtained. So in figure 13a shows the P versus PF. Figure 13b shows the V versus PF. So the blue line are the MGC requirement, and the orange line are the data collected. As shown in figure 13a and 13b, the results of P versus power factor and voltage versus power factor for no capacitor bank connected to the grid system show that the inverter controller can absorb and supply the reactive power, but it did not comply to the MGC requirement. These are the waveform of voltage, real power, and power factor obtained. As you can see at the voltage bus ABC, it is very unstable and not smooth, as well as the real power and power factor. So this is the result with 500 kVAR capacitor bank. This is the result of the voltage and current at the grid, voltage and current at the bus, as well as real power, reactive power, and power factor. So this is the result obtained. Figure 15a shows the power versus power factor. Figure 15b shows the voltage versus power factor. Just like before, the blue line is the MGC requirement, and the orange line is the data collected. As shown in figure 15a and 15b, the results of power factor, the results of power versus power factor and voltage versus power factor for 500 kVAR capacitor bank connected to the grid system show that the inverter control can absorb and supply the system and is adequate to comply to the MGC requirement. This is the result of the waveform for voltage bus ABC, voltage grid, real power, and power factor. As seen, the voltage bus with 500 kVAR capacitor bank is very smooth, as well as the real power and the power factor. So the voltage stability for no capacitor bank is unstable compared to the 500 kVAR connected to the grid system. As well as the waveform stability for real power and power factor, both for no capacitor bank is also unstable compared to the 500 kVAR connected to grid system. So the conclusion of this project, it is found that the solar power plant at FKE UTEM does not comply to the MGC requirement. The grid-connected PV inverter controller that could absorb and supply reactive power is designed. Next, the capability of the voltage variation of the grid-connected PV inverter controller to absorb and supply reactive power following the MGC requirement are also achieved. It shows that with the presence of capacitor bank, the grid system can comply to the MGC requirement. And lastly, the impact of voltage variation of the grid system to the PV plant with reactive compensator. which is the capacitor bank, is also studied. It shows that the voltage stability could not be maintained without the presence of a capacitor bank. The recommendation of this project: it is recommended to use a more advanced software than the MATLAB Simulink, as it will be more accurate and suitable for a larger scale of a PV power plant. Next, for further study, the VF control should be applied to a hardware of a PV power plant rather than through a simulation. Then the data obtained from the hardware can be compared to the simulation that was studied. And lastly, a static synchronous compensator could be used to replace the reactive power compensator, which I use now, which is the capacitor bank, to improve the voltage regulation. So that's all from me. Thank you.